All right. I hope I'm audible and you all can see me as well. Chandur, can you confirm?
Yes, Sahan.
All right. So let's start. So first of all, a very warm welcome to our very first webinar right here at the Technoid community powered by Search Global. So my name is Sahan Bandara and I'm a product manager at Search Global. And since there are people who's joining within Search as well as outside Search, I would like to give a small introduction to what Technoid is and what we are doing here basically. So Technoid is a public community powered by Search Global, and where our purpose is to share tech-related content to help people with their doubts and issues and provide them with a vast amount of information relating to, of course, tech-related industries. So we are currently working towards 3 different areas, that is webinars, then videos, and then blogs. So we are working on our Technoid Live website, that is technoid.dev, and that will be launched soon. And yeah, so basically the tech-related content is given through blogs, tutorials via YouTube, shorts, and public forums for people to talk. And basically, this is not just a platform where only people at Search can come. This is a public community, so anyone out there, anyone who's interested, you all can join with us, you all can conduct sessions, you all can contribute us with blogs and videos as well. So today, we have a very special person doing our very first session right here at the Technoid platform, who is Yasiru Ratnayaka. Yeah, so I would like to hand over the proceedings to Yasiru, so you can continue.
Hi, everyone. Thank you, Sahan. So I think we can get started. Let me start sharing my screen and we'll get onto it. Okay, I hope everybody's able to see my screen blown up. All right, without further ado, I wanted to get, talking about generative models. So that's the title of this talk. We will actually be looking at mainly what they are, a few key deep learning based generative models. And I will also try to finish with a bit of an illustration in JAX, which is a automatic differentiation library in Python. And if you're familiar with like TensorFlow, PyTorch, JAX is of a similar vein, but as you'll see, it's kind of hewing very close to NumPy and quite interesting and easy to use. In terms of the talk, I think Sahan gave a little intro, but in terms of Technoid, in terms of the audience, I'm kind of assuming that you would have a bit of a background in machine learning, along with some familiarity with Python and the numerical stack there like NumPy. What do I want to really cover? I want to actually focus more on concepts and try to make this about building a little bit of intuition, going over a little bit of the formalism. So there's a little, maths involved, but I think it'll be fairly clear from the intuition how you can, connect the two. And we'll also be down the line looking at an actual implementation in JAX. We'll go through a bit of a taxonomy of, different types of generative models that you might come across. And what are some considerations when you evaluate them and when you scale them up. We'll have a bit of a digression in the middle on deep learning and JAX. I'll try to introduce both with a little bit of motivation. And then we'll cover one particular type of generative model that actually was quite popular a few years ago, but now is kind of not the most popular of the lot, which are GANs, or generative adversarial networks. And I'll try to show you a little bit of an implementation of that. All right, so what are generative models? Well, you're pretty familiar with them already in terms of coming across them in real life. You've had very likely had a look at ChatGPT, which around January, I believe, had some 100 million users within some 2 months of its launch. These have really taken the public consciousness, and it ranges from things like thispersondoesnotexist.com to certain text image models like DALL-E 2. You've probably seen that, Stable Diffusion, Imagen, Midjourney, and the like on the text to image front, but also other types of cases where these models are kind of mimicking or generating data from known distributions. So a good example lately, a bit of a scary one, albeit, is voice cloning. There's both, good and bad that's being discussed in the public forum. So, for example, you might have concerns with models like ChatGPT and systems, really, whether there's going to be plagiarism in academics, or whether creative industries might be at risk, from writers to artists. And it's also easy to imagine, especially with these language models, how industrially you could now generate misinformation at scale. And you might even be perpetuating some of the biases that already exist in your training data. So if it's an image model, you can imagine that existing body image worries might be exacerbated, or that exist in terms of the language. There's no real reckoning for things like bias in the language, because these models are very data hungry, and the companies and the universities that build them may not necessarily try to de-bias them ahead of training. So there are these kinds of concerns, which seem kind of very immediate and practical, but there's also other concerns like AGI, and it's not really, and by AGI, I mean artificial general intelligence. And I've got a little comic for you on the left side of this, which kind of gives you a sense of the flavor. And really, it doesn't seem like science fiction anymore, with some of the capabilities of models like GPT-4, where they have evaluated on fairly practical things like the bar exam, AP calculus, AP biology, and the like. And part of that might just be that they have run out of training data, because some of these models require so much data, as I mentioned, that they've scoured the internet, and even some of the data sets that might be often used to evaluate them might actually be appearing in some form or another in the training data. So that's something they want to avoid. But at the same time, these new evaluation metrics are something to really consider in terms of how good these systems are getting. And it's really interesting that a purely generative system like the language model that is GPT-4 can have such an impact. So these are fairly powerful models, and I will try to give you a bit of a sense of what makes them so powerful, and what kind of uses that you can put them to. So, true to their name, generative models are really about generating new data points. You may have come across discriminative models in other areas of machine learning. And discriminative models, a good example is a classifier. You can see in this image on the right side, there's some handwritten digits, and we're trying to classify them into, are they 0 or are they 1? So on the left, you see this discriminative model doing so. So you have some sort of target label, which is the Y, and it's conditioned on the data. So given some data point, are you able to say, okay, this data point is probably 0? or this is probably a 1. So that's what a discriminative model does. It's really trying to separate the data space so that you can get at the labels that you really care about. In terms of generative models, by contrast, they're actually trying to model the joint probability. This is both X, which is the data point, as well as its label. And you don't necessarily need the label at all, because in some settings, like you can imagine unsupervised or self-supervised settings, you don't actually need a label. You can actually have the generative model try to come up with the distribution of X, right? You can kind of see that this is a much tougher problem already, because you can have this kind of separating hyperplane set up in the discriminative model, where you're having a very high, kind of, it could even be a high dimensional space, but you're having different planes basically cut it so that you're partitioning that whole space. Whereas here you now have these data instances, and you have to sample them. So your target, Ys, if you have them, the labels can be small, a small number of them. They're enumerable in the classification setting. But let's say that you're actually looking at trying to model X. So there might actually be quite a few data points that you have. But you might now be wondering, okay, if I pick a new data point from this distribution, what would that look like? So a discriminative model can perhaps get away with, trying to look out for certain telltale signs. So maybe the fact that there are circles might let the discriminative model know that this is a 0. And the fact that it's kind of a line at some orientation might give you an indication that it's actually a 1 in that case. But you don't have to actually consider what goes far inside the boundaries. You can just get away with considering what's happening at the boundary. But the generative model actually has to model quite a bit more. Different nuances of the distribution. So what kind of correlations can occur between instances of 0, and those can look alike. They can look slightly different. You can see this kind of crossed out 0 as well. Whereas a discriminative model doesn't really have to bother with these things. So the problem, you can kind of get an intuition, is actually fairly difficult. But we'll see how modern models kind of get around this. So looking into the formalism, and I'd like to kind of start on the right-hand side here. We're trying to start with some sort of data set. Let's call it D. We're trying to approximate some underlying distribution of this data. So according to that distribution, this data has been drawn. So every instance in D has actually been drawn from this P data distribution. And in particular, we want to focus on trying to approximate this P data distribution, which is unknown to us. We don't know how nature or some other process actually created the data. We may not know, and that's why we want to do machine learning on it. So what we want to do is try to find a parametric approximation, which is this P theta over here. And P theta is parametrized by these thetas. So there are a finite number of those thetas. And what we want to do is, for a particular sample X, the generative model should tell us, the one that we come up with should tell us how likely that sample is, how to generate that sample, but also ideally how likely that sample is. So P theta of X. So how might we go about it? If you're familiar with machine learning, most of it kind of boils down to some sort of optimization problem or other. And we can consider it in that manner. So we have these parameters, your thetas, and they're coming from a model family of interest, let's say, some family M, and we can approximate them with some, as long as you have some idea of distances between distributions, you can just say that, okay, your theta star, that's your approximation, is whatever kind of, whatever thetas minimize the distance between your true data, which is p data, and your approximation, which is p theta. So to do this, there are different methods. So in maximum likelihood estimation, you might be trying to maximize a product of likelihoods. So you can see here that it's you're taking every point in your data that's available to you, and you're just multiplying out these probabilities. So that's the likelihood of this data set altogether. And then this has some, you're assuming that it's something you can do in terms of multiplying them out. Otherwise, you have to condition them so they're independent, identically distributed. And what you tend to do with maximum likelihood, with the maximum likelihood estimation approach, is you're taking the negative log likelihood and you're minimizing it, because minimization is kind of how you pose this problem a lot of the time. But there's a challenge to this, because if you look at that problem seriously, it's actually intractable to come up with this p theta. So what you're actually going to be doing is you're trying to do some kind of approximation. So we may have some models that output probability, some models that don't, but ultimately you're trying to sample points from p data, some sort of approximation of p data at least. Usually you have your possible number of samples far outstripping the size of the data set that's available to you. If you think about images, for example, you might have each image having some sort of length, width, dimensions, and each and the multiplication of those, in terms of pixels, that will give you how many pixels there are. But each pixel now has 3 channels each. And it can take values on each channel. It can take values from 0 to 255. So now, if you think about that, it boils down to a massive number, 256 to the power 3 into whatever the length and width in terms of pixels of that image. So it's a really gargantuan number. Whereas even the biggest data sets of images we have these days, like ImageNet, only have on the order of millions of examples. And if you think about it from what's popular these days, especially, is NLP, as we talked about. So with NLP, you probably want to look at the number of possible subsequences up to, let's say, some sort of capping length n, formed out of some vocabulary of tokens or words. Let's say that's of size m. So you have, for any length k, you have m to the power k sentences, which are possible to generate. So it's n choices, and then for each token, and then k times, because it's k length. And then you want to sum this up from different lengths k, from 1 to your maximum length n. So that becomes like a massive geometric sum on the order of your vocabulary size m to the power n plus 1, where n is the largest possible sentence. So even massive data sets like what GPT-4 might be trained on, which is probably most of the public internet, can be easily dwarfed in size when you look at the data sets that you're looking at. So that's kind of the setup. And what we typically do when we try to put try to do this kind of estimation, we want to try to have some function that estimates this p data for you to create the p theta. So for p theta, we might want to look at a fairly expressive class of functions. And usually these days, it tends to be neural networks, which are very expressive. What you want to do is, because we said that p theta, it's kind of to directly calculate p data is intractable. We want to look at, different families of neural architectures that might actually help us help us try to approximate the p data in that way. So if you think about this in terms of why it's actually intractable, if you think about the law of total probability, you can see that, if you looked at discriminative models before, so you want to have the total probability being some sort of sum over the marginals into the conditioning probability. So whatever way you want to cut it in terms of discriminating, you're going to have to end up integrating over all possible target breakups in the discriminative setting. So that also gives you a little bit of intuition, I hope, in terms of how difficult it is to do the generative modeling. So one thing that's a bit of a saving grace for us, though, is that there's something called the manifold hypothesis. And this has some theoretical justification and some empirical justification that I'll let you, find out about. But the idea is that natural data sets tend to lie in low dimensional manifolds that are kind of embedded in a bigger space. So even though I was talking earlier about the space of all possible images, when you look at real images that you find out in the world, they aren't really going to basically span the entire spectrum of what's possible in terms of images. A lot of it is going to just present as noise. So with that kind of observation in mind, what you want to do is you want to try to generate data. So you can see kind of a recipe for this from OpenAI, as it happens, where they take some sort of noise. This is the unit Gaussian Z that they're taking, and they want to create some sort of neural network. So the idea of the neural network is that it's parameterized by theta, which are those parameters, the finite number of parameters, and they're going to kind of generate a distribution for us. And this can be in some image space, it can be in some sort of token space for natural language or the like. And what you have is a problem where you have one distribution and you have another distribution. And you need to try to create some sort of loss for the neural network so that the distribution of the true data can be well approximated by this generated distribution. And that's really the recipe for generative modeling. Behind all the formalism, that's kind of what's going on. Any questions so far? Okay, perhaps not. Okay, so bear with me. So let's look at some classes of generative models that we might want to consider. So like I said before, what you're really trying to do is try to get this density probability distribution, and then that's uniquely defined by density. What you want to do is try to take some approach where you're trying to approximate that. So there's generative models that kind of break into broadly two categories. So there's models that kind of have some explicit view on the density, and there's models that have some sort of implicit view on the density. And these can, break down even further into what's tractable, and that really just means kind of computable, as well as computable in an efficient way. This is computability-wise as well as complexity-wise. And then there's things that are approximately getting at the explicit density. And you can see some examples on the right here, where I've got as examples of tractable models, autoregressive models. So the autoregressive family actually contains models like large language models of the vein of GPT-3 and GPT-4, as well as some models that you might have heard of that really rely on kind of conditioning over time. There's also what are called flow-based models. So the idea here is that if you have some sort of data point, you can actually create some sort of flow, and that's typically, let's think about it as a neural network. It's some sort of function that ends up reducing that to noise, and then from that noise you apply the inverse of that function, and you end up with a reconstruction of that data point. So you can imagine that by parametrizing this and kind of doing this over and over, you can actually learn a good flow and its inverse. And of course, you might be familiar with approximate explicit density methods, including variational autoencoders or VAEs. So in this diagram, you can kind of see the idea here, where you have some sort of encoder structure. You go into and this encoder structure comes out with parameters. And these parameters are really parameters for a distribution. And this distribution is what these random samples are drawn from. And what you do is then you try to reverse this process. So you take your parameters that the encoder comes up with, you take your Z, and then the decoder's job is to try to come up with some sort of reconstruction of what might have been fed originally into the encoder. And you kind of see this pattern over and over in generative learning, where there's some sort of encoder and decoder. And you can kind of see, although the name changes for some of these other models, it's really the same type of process. And you can also see that with the Z, there's some idea of randomness being brought into the picture. You may have also heard of diffusion models, so they're kind of related. They're also a approximate explicit density model. The idea is you take your original image, you try to learn how to add Gaussian noise step by step. So Gaussian noise is noise from a normal distribution. You add it step by step, and how to both add it, and which is trivial, but you learn how to reverse it. So until you come to this completely random image, random static rather. And by learning the reversal process, what you can do is you can do a kind of forward pass where you take some random noise, and you know how to add image noise on top of that noise to progressively get at a realistic looking image. So that's a little overview of some of these models, and you want to kind of you want to kind of also that usually these networks are fairly really isolated to this Z, which is we're very explicit and in control about adding that randomness. So the other point to note is, I think we talked about the manifold hypothesis. The other idea is that, and it's kind of drawn in this diagram from Lillian Wang's blog, where you have these kind of smaller block representing Z versus the X over here. It's only different in the diffusion model, but typically this is also a recurring pattern where you have some sort of smaller representation of your original high dimensional space, and you kind of have this bottleneck, and it's from this bottleneck that you grow it out. And this is really explicitly the manifold hypothesis in action. So you've got these different types of model classes. And what we want to think about then is, and we tried to provide a bit of a taxonomy of how they break up. I think the one that I didn't talk about is kind of this autoregressive model. So what happens in the autoregressive model is you're kind of looking at you're looking at this kind of maximum likelihood type of setting, but you're assuming that every variable, and you can see it in this Bayesian network diagram here, every variable is kind of conditioned on every variable that came before it. So there's a explicit sense of sequence here. So x2 comes after x1, and x3 comes after x2 and x1. So each of these things, for given xn, its immediate predecessor, as well as all its prior predecessors, have some sort of impact on it. So you can imagine this as a whole bunch of conditionals. And these models are actually what get used up in what get used in large language models these days, like GPT-4. So you can kind of see in this next slide what that looks like. So on the left, you actually have a interesting diagram from animation, really, from a Microsoft research blog, where they've looked at the number of parameters, and you can see this is in the log scale, but it's still scaling up quite, almost exponentially. And this is over time. So you can see some of the model classes we talked about, like the VAE and the GAN, are there. And in the light blue, where it says NLM, these are the kind of autoregressive models. And you can see that over time, they have some fairly big GANs going on, including one that is literally called Big GAN. But over time, you have these autoregressive models being trained with more and more parameters. So that's just an interesting way that research has evolved. But there's also some, natural questions we can think about in light of this, like which models might scale better than others. And we have some natural questions about the inference on these models. So the first question you might have is, how do I actually take a new data point? Maybe I take noise, and using that noise and using that function that we learn, how can I generate a new data point? Is it actually something easy or hard from a computational perspective? So that might really matter if you're serving a model, for example, to millions of users, like in the case of ChatGPT. It might be a significant consideration how easy it is to infer. And for some models, especially those explicit density models, how do you get a probability out of this? What kind of probability can you assign to a data point that you did generate? Is this kind of sensible? Because if your approximate distribution, your p theta, gives you high probability on a generated data point, does it actually look like it could have come from your original data distribution? So it's kind of difficult, because in order to quantitatively evaluate this, because you have a lot of different types of models, some of them explicitly looking at a density, others implicitly doing so. But how do we actually try to match our mental image of, okay, this looks like a good synthetic data point that could have come from this distribution with some of the metrics that these models actually come up with? It's a bit of a non-trivial problem, and there's some trade-offs that you need to worry about. You might also wonder how controllable these things are, because are you learning something that is disentangled in the representation space? So we talked about maybe there's a lower dimensional manifold, but in that manifold, do you have the ability to control some high-level features? So let's say that you train a model on pictures of animals. So can you actually get high-level features like the breed of the animal, what kind of years it has, maybe if it's a cat or a dog, what kind of breed is it, what kind of tail it has, those sorts of things. Can you pick those out easily? And by picking them out, maybe can you control them? And also you might worry about what sort of training dynamics come into play, but we'll see a bit more of that when we get to the GANs. But at this point, I'm going to take a little breather and ask if there are any questions from the audience. You can raise your hand, or you can type something into the chat. We're having a look. All right. If no questions, and feel free, while I'm speaking, if you have any questions, just to pop it in the chat, and we'll look at it on the next slide that I look at questions. So I wanted to take a brief digression into looking at how does we talked about neural networks being the typical choice of parameterizing these approximate distributions. So how does deep learning actually work? So we have this kind of setting where you have some sort of vector input, you want to get a vector output, right? And to be very concrete, this vector input could be a vector that represents an image. The vector output could be the likelihood that it is a cat or a dog. So it might be in the cat category, you might have some sort of likelihood. In the dog category, you might have some likelihood. So you're trying to come up with this input and output, your X and Y. What we are going to try to do is, in this case, I'm going to show you what's called a multi-layer perceptron. So you have some sort of function that you can keep applying to your input and composing it so that by the end, you've applied your function n times. You're kind of keeping track of it. These are kind of linear functions. So you're kind of translating it in its space, you're kind of rotating it, that kind of thing. You might be mirroring it, that kind of thing. But then you might also look at an affine function. So this looks at slightly kind of moving your function. So you might not just be rotating, you might also be translating. And then you're trying to add on top a little bit of a non-linearity. So what you ultimately get is something like what you have in this picture. So your X is the input, it goes in. And then you have this kind of G, which is the kind of affine function. It's multiplying by some weight vector, it's adding some sort of bias. And then you have this kind of non-affine piece, which is the non-linear piece rather, which is going to kind of transform that linear function in some way. So you can think of it, if you've come across neural networks before, this is kind of your linear layer, and this is kind of your ReLU or sigmoid or tanh layer. And you have multiple functions like this, right? They're kind of composed together. And you have these W1, B1, those are really your parameters. So the thetas we kind of talked about before, very similar to that. So what you do is you take some sort of loss function. So this loss function is taken by looking at the input as well as the expected output. So the output might be something that you saw in your real data. And the function is kind of the composition of these things that you learned, and you applied it on X. So that's this F hat here with the parameters that you're learning. And what you want to get is what is the distance between these two things? How different are they? So some notion of that distance can be taken, and that's your loss function. And here it's just like a two norm. So what you want to do is try to find these parameters W and B such that the variance is kind of minimized in this loss function. So you naturally have the question, how do you actually do this? There's a mathematical way to do it, which is called gradient descent. So what you do is you take a gradient of this loss function. If you're familiar with like high school calculus, you can kind of take a function, you differentiate it, you kind of set that to 0, and then you solve for the parameters, and that kind of gives you the minima and maxima. So you do something similar. And then with that gradient, you know the direction of the rate of change. So you just step forward into that direction in steps of this eta at a time, and you should ideally find the minimum or maximum that you're looking for. In this case, you want to minimize this loss so that this network is performing well. So how do we actually compute this gradient? Here's a little bit of pseudocode in terms of if all the maths kind of bothers you. So you have some sort of affine function. It's literally doing a matrix multiplication here. I'm using NumPy here, and you have some sort of nonlinearity here. It's something called ReLU, the rectified linear unit. So it's usually 0 until it kind of comes to positive x's, in which case it's x. So it's a nonlinearity, and you've got some sort of loss, and you're trying to perform these gradient steps, and you can kind of iterate over this over many steps, and you can find out what these W and B rather should be. So how do we actually take the gradient? We talked about differentiation from high school. So there's like two flavors of differentiation we can look at. We can look at symbolic differentiation, which is kind of the cartoon that you see on the left here, which is what you did as a student in school. And there's also, and you can kind of program that procedure in, right? There's an example of this here on the right that I've given you based on SICP. But there are certain problems with this approach. For example, how do you capture something like control flow in this situation? And it might also be a little bit expensive, because a lot of the time you don't actually have very nice closed form formulas. So you're doing this for some big expression, and then you're trying to break up that expression. Maybe it's easier to actually keep track of some sort of gradient throughout of each sub expression and kind of put it together. So one other option is numerical differentiation. And in numerical differentiation, what you did is you looked at the definition of what is a derivative. It's you take the function of and you kind of add a little bit of noise, and then the function without the noise, you look at the difference, you scale that by the noise, and you try to limit that noise to 0. So you can empirically do this by kind of writing something like this, and your edge kind of iterates to be smaller. But computers use floating point arithmetic. So a lot of the time, because derivatives might be multiplied with each other, you're going to get a lot of numerical instability. And it's going to be kind of difficult to do this for higher dimensional functions as well. So there's a solution to this, which is called automatic differentiation. So in automatic differentiation, I'll kind of show you an example of how to implement it with something called dual numbers. The idea is probably more important than the explicit way of doing it that's illustrated here. So what you're trying to do is, in this case, you're considering not just real numbers, you're considering numbers of the form a plus b epsilon, where epsilon is some non-zero thing, but it in your arithmetic, if it's floating point, you can kind of think about epsilon squares to be 0, but epsilon is non-zero. So it's a bit of a suspect kind of thing to do mathematically, but it really does work out. So if you look at these dual numbers, you can actually compute you look at this kind of dual part of it, and that kind of gives you the derivative that you're looking for. So here's an example with, x plus x squared evaluated at 2, and that you can verify kind of works out correctly. So you have, this is an example of what's called forward mode automatic differentiation. There's also reverse mode that's used a little more frequently, and it's implemented here a certain way, but this is not actually the implementation you'll find in libraries like JAX, but it's really automatic differentiation that's enabling these things under the hood. So in terms of what is JAX, JAX is something that actually provides a easy way of computing this gradient for you. And moreover, JAX is a library that replicates some of the NumPy functionality. So if you use jax.numpy, you can import that as NP, and most of your NumPy functionality should work. The nice thing, though, is if you now create other functions, and those differentiable parameters in those functions are in the first argument, what you can do is you can differentiate through them just by calling this grad method on that final loss. And you have ways to kind of map over different losses as well. And there's a fair few methods, but I won't really go into it. But JAX is a very low-level library, kind of like NumPy. Whereas if you want to build neural networks, you might want to look at some libraries that are built on top of it. Think of TensorFlow being kind of like JAX versus Keras. And it's at a kind of Keras level that you see other libraries like Stax, Equinox, Haiku, Flax, and the like. So with that kind of bit of a digression, I just want to take some time for questions, if there are any. All right, there don't seem to be. All right, so it's a little bit of a digression over there, but let me get into trying to illustrate an actual generative model with this kind of setup. So you can see here GANs. So what is a GAN? Well, you're kind of seeing it right now in the diagram. So a GAN is a type of neural network architecture. The interesting thing about it is, as you might recall, it's kind of an implicit density architecture. It doesn't actually try to go about trying to get the density directly. They're what GANs are kind of what are called likelihood free. So they don't really bother with the likelihood question directly, but what it does come up with, you can kind of look at through a likelihood lens. And I'll kind of go into how that might be interpreted as well. So you have this kind of network, and I want to look at this diagram here where what you're doing is you've got a latent space. So this is where you get your randomness. So it's these Z's, and they might be, might be sampling them from uniformly, you might be sampling them from normal distribution. What happens is they go through this generator component, and then you end up with a sample. So this is now your kind of synthetic data point, because you didn't actually get it from the real images down here, but you can actually get a data point from that set of real images, your X's. And what you want to do is you want to feed them both into what's called a discriminator. So you have the real image, you have the real image down here, you have the fake image, which is your GZ, which was generated out of noise through the generator. And that's the one that learns, that's the generative model part of our GAN. And what this discriminator does is it's kind of playing a game with the generator. It's trying to say, the generator is forwarding, okay, here's my best fake, and it's not saying it's a fake. And the real images, you're getting samples as well. The discriminator's job is, how do I find out if a given sample presented to me is real or fake? So when it does so, what you can do is you have some sort of generator loss, you have some sort of discriminator loss, and these kind of go into the expression and you iterate again. So it's kind of a standard type of idea, but you have this kind of min-max game because now you have your thetas like before representing the generator G. So these thetas are parameterizing the generative model. So you can see the generated images in this part of the training objective expression here. They kind of, what's good for it is to kind of get the discriminator to misclassify. So if you look at the discriminator loss, you can see that you're trying to maximize something. You're trying to maximize when the discriminator classifies a real image as real, and the discriminator is further maximized when it classifies a generated image as generated. And the generative model kind of works the opposite way. So it's a little tricky because now you've got these two things playing a game with each other. But the way to actually train this is not too challenging. What you do for the training algorithm is something like this. You iterate over different your data set many times. So these are called epochs. And what you do is you sample a mini batch of some data points. These are real data points from D. And then you also sample a mini batch of some noise data points, your Z's, and that's from some sort of noise distribution. What you want to do is you want to take a gradient descent step because you're minimizing on the generator parameters theta based on this. So you can kind of think about turning this into a more discrete expression and stepping that way through the gradient. And once you're done doing that, you do another gradient. This word should be ascent here because you're maximizing. You're taking a gradient ascent step because you're maximizing on the discriminator and on its parameters phi. So you're kind of updating by turns. So there's some good things about this system. For images, for example, this was really the first kind of architecture that gave you really high fidelity images that kind of made you go, "Oh, that should be a real person," but it's actually not. And that high fidelity is one of the pros for it. You also don't have to worry about some of these likelihood questions. You have a very practical way of getting the model to approximate it in a very implicit way. So those can be considered as pros. On the con side, there's a few. So sometimes you might have the discriminator being a little too strong. So your signal from the loss function gets a bit weak. So the generator kind of stagnates. So you might have the discriminator kind of perfectly learning how it can tell the synthetic and the real apart, but the gradients that it sends out to the generator kind of vanish completely. So now you have this situation of vanishing gradients and your generator doesn't actually improve. You could also have a situation where the discriminator and the generator can kind of get stuck in some sort of local minima or local maxima, and it doesn't actually get to convergence. So that can happen. There's also the opposite of the first point, which is where the generator overpowers the discriminator. So this can lead to what's called mode collapse. So if, for example, you get a very strong generator, maybe it tries to actually replicate a single observation from the data. This would be your mode. And this kind of observation would continue fooling the discriminator many times. So every kind of, if it notices that it's getting good results through that loss, the generator will kind of keep presenting the same image, and you end up with just one image or just a few images, so it kind of collapses into a mode. So this kind of situation could also occur. And it can be kind of difficult to correlate the loss with the sample quality because the loss is kind of this minimax game. So is it really the case that, the smaller the loss on the generator, the better the quality of the images? Well, that loss on the generator is really dependent on the capability of the discriminator at the time, which can kind of keep improving as well if your system's kind of playing along nicely. So in that case, maybe you might still get high loss, and your generator might actually start getting worse in terms of the loss perspective, but actually you're getting better quality images. So it's really difficult to get a metric there. And you might also have this case of entangled latent features. I think we talked about how can you get the representation to be disentangled so that you can, control certain things or know when certain things will appear. But in GANs, this is kind of a challenging problem. There have been, certainly for all of these cons, there has been a wide amount of research going on. It's a vast area. And a lot of them have been, a lot of proposals have been made to alleviate any one of these. But it's, again, a kind of vast area, and there's a lot of empirical work going on. And some of these are a little more hacky than necessarily solidly, principled, theoretically sound kind of things that have happened. But certainly they do work to make this system capable. So how might you do this in JAX? Actually, before I do that, any questions about GANs? All right. No, I think no. If none, let's kind of move on to what does that implementation kind of look like. So I've got a bit of code, or it might be even pseudocode really, because what I've got here is, what I've got here is on the left, how you might create some neural networks out of JAX. So you can see it's fairly simple. These are kind of, again, linear perceptron type of setups. So you have your G and your D on the left. So G takes some parameters, your thetas, D takes some parameters, your phis, and G also takes the noise component Z, and D also takes the image, which is X. So you can kind of see with the dot product, you're very easily doing that kind of affine linear transformation. And with this ReLU function, you're very easily doing this nonlinearity that you're placing on top of it. So what happens with the G is that you're actually doing another dot product with the X. Sorry, I should probably rename this. But yeah, you're kind of doing another dot product, so you're ending up with a with an output that's kind of like on the image dimensions. Whereas with the D, you're kind of trying to come up with an output that is more along the classifier dimension. So is it a generated image or not, is what it's trying to do. But it's fairly simple to do this. And you can see that these functions you can just directly apply. The only difference to this being NumPy would be that I've used JNP instead of NP, but it's exactly the same thing. You import jax.numpy as JNP and try this. And on the right, you have the losses that we just talked about. So I've kind of defined a binary cross entropy function as a kind of helper function. But you can look that up later. But it's exactly what we showed in the GAN slide before. But you have basically this binary cross entropy for the discriminator loss components, the X loss and the GZ loss. And what you do is you sum them up, and that becomes your discriminator loss. Whereas on the generator side, I'm importing NumPy here. This is the original NumPy, and I'm just generating some random vector. And then I'm trying to create the by sending it through this generator network. I'm trying to create that same loss. So you got one binary cross entropy term over here for that loss. So finally, and the easy step actually is the taking of derivatives here, because you can just say, okay, from JAX import grad, the discriminator loss grad is just grad of this D loss. The generator loss is just grad of the G loss. And that's pretty much it in terms of defining the networks and losses. Once you have that, the training loop, which I just showed you in pseudocode, looks very similar. So for every epoch and whatever number of epochs, you might have to go through batches. So this is the example is around image generation, but you kind of go through these batches. But what you do is over the training set, you alternatively go through discriminating as well as generating, and you keep doing this gradient update over here. And this procedure is pretty much what the GAN is all about. So you might want to consider a reasonable stopping time, and you can then start generating your own images. So that concludes what I had for you today. There are some references and resources that I've just listed out here. But do we have any other questions at all?
Right, thank you. So I'll just unmute the chat, unmute everyone so that, yeah, that you all can ask any questions if there's any. Okay, check now. You all should be able to talk. If there's any questions, you all can ask now. Or just simply use the chat. Yeah.
Awfully quiet. The one additional thing to mention is I will actually share a bit of Colab notebook with that JAX example, so you can kind of get your hands dirty and try to play with it. You might have noticed that I just use functions. There's no kind of classes or anything. JAX is a very functional first kind of library, so you can get away with a lot purely with just functions, and you can get a sense for that yourself by playing with the Colab I will share.
All right. So shall I take over, Yasir?
Sure thing. Thanks, Anand.
Okay then. Yeah, so thank you so much, Yasiru, for joining with us today at our very first session of the webinar component of Technoid. And yeah, so this is just the first session of many sessions yet to come, and we'll be organizing more sessions in the future, in the upcoming weeks as well, and we'll be publishing them into our social media plus the website as well. So just go to Instagram, search technoid.dev, and you all can follow us for any updates. And once again, thank you so much, the head of data science at Search Global, Yasir Ratnayaka, for joining with us and sharing your knowledge on generative models today. And next week also we do have a session, and we'll be announcing that in our social media. So, and the recording will also be available on our YouTube channel, Technoid. So please subscribe that as well. So thank you so much, and have a good evening ahead.